Hello and welcome to Coffee Zen. Today we will be talking about the world of quantum computing. What is quantum computing? Put simply, it is a very powerful computer, even more powerful than the most powerful supercomputers that exist today. And you might ask yourself, all right, what does it mean? What makes it different than a normal computer? Well, there's a couple of key aspects that you might have to understand first. The first one being quantum physics or quantum theory. And again, for any hardware engineers and physicists and whoever's listening that has a mathematics background and degree, I apologize for the oversimplification of the concepts, but bear with me. I'll be simplifying it as best I can without spreading false information. So, quantum computing. Quantum computing is based on the theory of Edward Schrödinger, which he proposed back in the 90s, was the theory of superposition. Now, superposition is a theory where a particle can be positive and negative at the same time until you measure it. Now, to explain this in an analogy, I'm going to use the same analogy that he used. That is where the famous Schrodinger's cat comes from. Now, if you have heard of Schrodinger's cat, it basically revolves around the theory of if you put a cat in a box and you have two vials, one filled with food, the other filled with poison, and you put that cat in a box and you close that box up, from the observer's point of view, that cat is alive and dead at the same time until you physically open the box and you look. Then you have confirmation of what that cat is. Now, the maths around this is extremely complicated, and I won't go into the details of it. Myself, I don't even understand all of it, but the basic principle carries over to computer science. So, the basic principle that carries over to computer science is it being in a superposition. So when you write a PC program or when you write a program, you compile that program. That program gets compiled into machine code. Machine code gets then compiled down to binary, ones and zeros. And that then essentially tells the computer what resistor to switch on and off. That is how you carry a message, for example, over into a PC. So if you tell if you click save a document on my PC, it will then write that to your hard disk in the forms of ones and zeros, either the resistor being open or closed. Again, there's a lot of more complexity around that. Binary gets translated to hexadecimal code, which is base 16, gets then translated to upper level computer programming languages, which is C or C++. Again, I don't want to confuse the listeners to go into too much details. If you did not stick with me through that explanation, it is very simple. If I click a button on a PC, for instance, if I click a G, there's a set of resistors in the PC that's going to be on and a set of resistors that's going to be off. That is how the PC knows that I've pressed a G. The concept of quantum computing takes that to the next level, where it says that I have one resistor that relies on, it's either gonna be a 1 or a 0. It is gonna be both until I measure it, until I look what it is. It will be consistent of a superposition. That is where the term comes from. It's a 1 and a 0 at the same time. This carries over, so it was a theory for a very long time, but IBM has recently built the first ever quantum computer. Google is busy doing the same. They've already compiled a 8-bit program, which consists out of 8 bytes. It's a very simple program. It can't do anything powerful. This impacts your life, your daily life, so dramatically. Reason being that quantum computer will be the future resource we use to compute things, mathematics, for instance. Your bank's encryption, right, is based on a specific algorithm. An algorithm that makes it very hard for third-party people to guess your password, your PIN, whatever sort of authentication you use. It is very hard to guess. for good reason. I mean, you don't want anyone to know how to log on to your bank. I'm using it in very, I don't want to use the word fear mongering, but that's not at all what I'm doing. I'm just trying to get a concept across. Quantum computers basically provides us, again, not yet, but in the future definitely will, to crack that authentication code, that algorithm. It will be very easy for a quantum computer to guess, because it can do a lot more calculations in a smaller amount of time. And I suggest, if you're interested in knowing more about this concept, do research on your own, watch a YouTube video. I'm just giving a very brief overview of what I understand the concept to be. To pull it back to reality, or to pull it back to now, currently we have supercomputers that resides at institutions like the government, or research facilities, or universities. All of them have supercomputers. But the reason why what I'm advocating, or what I'm trying to explain here, is that in the future, because quantum computers are now where computers was back then when they sent the first rover to the moon. It is the size of a literal room. It is a very, very big piece of equipment. But in the future, we will be able to have that power in the palm of our hands. And this is where the fascination comes in, that you'll be able to solve the most complex math problems that exists to this day. Something simple, well, not simple, but something that should be considered very simple, is protein folding. What is protein folding? Protein folding is a whole different discussion, but essentially what it means is that if you can fold proteins, if you can predict how proteins will be folded in a certain way, you can literally cure cancer. Yes, I am not exaggerating. It is literally that powerful. If we can crack the folding protein problem, then we can literally cure cancer. We can go as far as, if we can predict protein folding, we can predict viral outbreaks, certain viral strains, and we can prevent it from happening. This is a very oversimplification of what I'm trying to get across, but the concept stays the same. I'm trying to explain that once we have quantum computers available to every man, or to every normal day, the landscape is going to look totally different from what it does now. And it already does. I mean, our phone's processor is a million times stronger than the processor they used to send the first manned mission to the moon. I mean, if you look at the strides computer science has made over the years, and computers in general, I think you would be in awe to think that we were there and now we are here. And I think once you have understood that, then the future looks very exciting and a bit scary, I would say. I think basically that if the quantum computer becomes a everyday reality, we would have a very interesting civilization in front of us. Just to give you another example of the complexity that a quantum computer would be able to solve, is a simple example of the travel salesman problem. Or not, let's not even go to anything specific, but there's this concept in mathematics and in computer science that we have N versus NP, right? So again, I don't want to drill down too much into it, but just give a brief overview. And if you're interested in learning more, maybe in future episodes I can go into more detail. But please leave a comment on this. If you're listening to this on YouTube, leave a comment. If you downloaded it, go back to the Podbean website and download it and give it a listen. So basically, the concept of N versus NP is that you have a set of mathematical equations that is easy to solve in real time. I'm talking multiplication, division, plus, minus, and anything complex as that can be solved in real time. And then you have insanely complex problems that cannot be solved in linear time. Its complexity increases dramatically as you increase the size of your data set or your parameters or even your actual calculation. An example of an NP problem would be something like the travel salesman. And you might ask, what's that? Well, it is essentially this problem proposed that you have a person, or a salesman, if you will, that needs to visit a set of specific locations, each location being a variable distance away from one another. And to solve this, you must find the optimal route the salesman must take in order to minimize or maximize sales or minimize the cost it costs him to travel to these locations. And this sounds very easy to do, but once you increase the complexity of the amounts of nodes the person must visit, it becomes increasingly difficult for a computer to solve this. And then you move into the realm of brute forcing, which is basically trying every single solution until you find the most optimal solution. And this might not sound like the optimal solution to find the optimal solution, but it is currently the only solution that exists to solve this problem. And quantum computers can decrease the complexity of this problem, that the cost of processing this data, if you will, very much there. It is very easy to solve. And quantum computers' aim is to increase the processing power so much that it is easy to solve, and maybe even prove that the travel salesman problem is not even a version of the NP problem, but maybe a version of the P, maybe in the P realm. And the P realm being stuff like multiplication. And we know what the process of solving a multiplication equation is. We take the one value and we multiply it by the other value X amount of times. A simple example is like, we know that 2 times 2 is 4. It all comes down in mathematics to prove. How do we prove that this route that I have calculated for the salesman is the optimal route? Well, I have to then basically redo all the calculations to prove that answer is correct. There's not a simple way to prove that my answer is correct. I have to basically redo the equation to prove that my answer is correct, where in something like multiplication, I can use addition, a whole other method, to prove my multiplication was correct or done correctly. I can use division the same way. I can use the answer of the division sum multiplied by one of the values in the division, and I can get the multiplied answer would be my one factor that I have divided it by. And again, this might come off as very complex. It is not. It is actually truly amazing to think about the possibilities that quantum computing might have in the future. And please, I encourage you, go learn more, go research more into quantum computings. Have a discussion in the comment section. If I made a mistake somewhere, point it out, comment, like, subscribe. I've noticed that a lot of you guys are not subscribed. Please hit those subscribe. Let's get those numbers up. Thanks everyone. Have a lovely day and enjoy.